A tumor is not a static monolith. It is a constantly evolving ecosystem. Treating it means trying to hit a moving target, where malignant cells constantly mutate, divide, and develop varying levels of resistance to the drugs meant to kill them. To model this mathematically, we assign a continuous trait to the cancer cells, ranging from 0 for drug-sensitive to 1 for fully resistant. As the tumor grows, biological parameters like natural death rates and mutation probabilities constantly alter this population density distribution. The total tumor population at any given moment is simply the mathematical integral of this density across all the different resistance traits. Finding the right drug dosage requires minimizing a specific cost-functional equation. This forces the system to balance two competing variables, minimizing the total tumor burden at the end of treatment while strictly limiting the cumulative physical toxicity of the drugs. Managing heterogeneous cancer means solving a dynamic, multi-objective optimization problem across a continuously shifting parameter space. The traditional method for solving these optimal control problems is Pontryagin's maximum principle, or PMP. To work, PMP must integrate a costate equation, a set of variables representing the marginal cost of the tumor states, derived from a mathematical function called the Hamiltonian. But a tumor dynamics model creates a highly nonlinear, multimodal mathematical landscape. If you visualize this parameter space, it looks like a complex three-dimensional surface, full of peaks, valleys, and local minimums. PMP relies entirely on a precise initial guess to navigate this surface to the optimal solution. In high-dimensional spaces, a microscopic error in that assumption causes the trajectory to wildly diverge off the manifold entirely. Because of this extreme sensitivity, PMP frequently suffers catastrophic convergence failure when applied to complex, mutating tumor models. Standard fixed-dose protocols and basic heuristic scheduling methods also fall short because they lack the ability to adapt to real-time tumor evolution. To calculate a truly optimal dosage schedule, the computational architecture must separate the global search for the solution from those fragile initial costate assumptions. This brings us to a two-step hybrid approach designed to bypass the traditional costate integration trap. The first step utilizes quantum particle swarm optimization, or QPSO. Classical particle swarm optimization relies on particles moving with strict deterministic velocity vectors. QPSO abandons those strict vectors, instead modeling particles as quantum entities that sample the space using quantum potential fields. By adjusting the characteristic length of the potential well, these quantum particles can effectively tunnel out of steep local gradients and map the true global minimum of the topological surface. Because this global search mechanism does not rely on gradients or costate integration, it operates successfully regardless of the initial starting conditions. When we apply the QPSO algorithm to a two-drug regimen, this chart displays the resulting raw control inputs over time. It shows two highly erratic, rapidly oscillating paths for the drug concentrations. While visually chaotic, this raw control policy successfully identifies the optimal dosage envelope within the mathematical simulation. However, the raw output produces a high-frequency, bang-bang-style jitter, where the dosage spikes up and down instantly. Administering this rapidly oscillating dosage schedule is physically impossible in a clinical setting and would be highly toxic to a human patient. Meta-heuristics possess the mathematical power to find the global optimum without costate integration, but their raw outputs are too chaotic for direct medical application. That requires the second step of the hybrid architecture: regularization using a nonlinear programming solver known as fmincon. The chaotic, raw output from the QPSO algorithm is fed directly into fmincon to act as its initial condition. This secondary gradient-based solver applies strict mathematical smoothness constraints to the data. The jagged, oscillating data lines are refined, morphing into smooth, continuous curves that represent practical control inputs. When we overlay the resulting tumor population dynamics onto this smooth control input chart, we see a sharp, continuous decline. The regularized curve achieves the exact same therapeutic efficacy as the chaotic global search. But a smooth line is not enough. The system must mathematically prove that this new, refined trajectory remains an optimal solution. We verify this using the Hamiltonian optimality check. These two stacked charts evaluate the first and second derivatives of the solution. The top chart shows the first-order check. It verifies that the gradient of the Hamiltonian with respect to the control variable stabilizes near zero, which is a necessary condition for mathematical optimality. The bottom chart shows the second-order check. It confirms the solution is a true minimum by proving the second derivative is positive definite, remaining entirely in the positive value range. Chaining a heuristic global search to a gradient-based local refinement successfully bridges the gap between pure computational mathematics and a clinically administrable protocol. With the hybrid solver mathematically verified, we can test it against a simulated 10-year treatment horizon. The focus here is analyzing how different mathematical functional forms of drug efficacy suppress the mutating tumor traits. The study evaluates 3 distinct modulation strategies to distribute cytotoxic effects across the tumor's resistance traits. The first strategy is a cosine-Gaussian combination. It pairs a broad periodic cosine function to suppress traits evenly with a Gaussian function focused tightly on a specific subset of traits. The second is a cosine-sine contrast. This alternates 2 periodic functions, ensuring different tumor traits are targeted at different phases of the treatment. The third is an exponential Gaussian mix, which uses an exponential decay function to target lower trait values early, combined with Gaussian intermediate trait concentration. The geometric shape of the cytotoxic function directly dictates the evolutionary pressure applied to the mutating tumor demographic. These 3D plots track tumor populations over 10 years. The top and middle plots, cosine Gaussian and cosine sine, show uniform flattening, distributing drug impact evenly. In contrast, the bottom exponential Gaussian plot retains an elevated ridge, indicating a surviving resistant subpopulation. A 2-dimensional cross-section at year 10 reveals a stark difference. The cosine strategies produce low, flat lines, while the exponential strategy spikes. That spike represents a dense cluster of localized resistance surviving the exponential decay. Monotonic functions like exponential decay target specific traits effectively, but they allow untargeted populations to survive, adapt, and mutate without adequate evolutionary pressure. The cosine Gaussian and cosine sine therapies achieve uniform, broad-spectrum suppression, leaving no safe harbor for resistant traits to hide. Defeating tumor heterogeneity requires non-monotonic, periodic combination therapies, designed by a hybrid optimization framework robust enough to map the tumor's entire mathematical complexity without breaking.